double integral over a rectangular region is defined this way. I want to take a look at this a little more precisely. Like, what the heck do you mean the limit as both m and n go to infinity of this thing, right? So recall. Now, some of you that are going to be engineers are going to kind of grumble and groan about this a little bit, but back in Calc 1, we gave a definition of what we mean by a limit. Remember, we said that L equals the limit as x goes to a of f of x if, right, remember this definition? Probably not. That's why I'm reminding you of it, right? If for each epsilon bigger than 0, epsilon bigger than 0, there exists delta such that if, actually let's put the if down here, if 0 is less than the absolute value of x minus a is less than delta, then the absolute value of f of x minus L is less than epsilon. Now you probably are saying, whoa, I didn't really get this the first time. Well, this is why I'm doing it again, because I think you have enough mathematical sophistication now to understand this, right? Notice, f of x minus L is saying that's the difference between these two values. I'm claiming that the limit as x goes to a of this function f is L. So I'm saying that f is getting really close to L, that this difference is less than some epsilon. That is, I can make this, no matter which epsilon I choose, that this difference is going to be smaller than epsilon, provided that is, if the x minus a is less than delta. Well, of course, x minus a is the difference between x and a. So if x is close to a, at least no further than delta away, then the function value and the limit will be close together, right? So that the function will be close to the limit. This is what the definition of the limit as x goes to a was. We also had L equals the limit as x goes to infinity of f of x if for each epsilon bigger than 0 there exists capital N such that if x is bigger than n, then f of x is close to L. How close? Well, no further away than epsilon. Right? No matter what epsilon you choose, if I can always show that once x gets big enough, once x is bigger than n, then the function and the limit are really close together, then I have the limit. Right? L is the limit at that point. Okay? This is what I'm looking at here. I'm looking at a limit as stuff is going to infinity. So for us now, we want to find capital N so that for both n bigger than capital N and little m bigger than capital N, so both m and n are bigger than this n, then the difference between the actual volume here and our estimate here of the sum I equals 1 to n, the sum j equals 1 to m of f of x I y star y I j, did I say I y? I j star y I j star. Let's come back here. Delta a. That this difference is less than epsilon for any epsilon. I didn't say this quite right. That is, for each epsilon, you can find a capital N, so that if little n and little m are bigger than that, then the difference between the actual volume and the estimated volume is as small as you wanted it, right? The epsilons and deltas are just measures of how close do you want to be. Do you want to be within 0.01? Well, then you might need capital N to be 1,000. Do you want to be within 0.001? Well, then you might need capital N to be 10,000. Do you need to be within 0.0000001? Well, then maybe you need capital N to be 1,000,000. I don't know, right? But the thing is, if you set a standard for closeness, epsilon, no matter how close you choose, no matter what epsilon you choose, if I can always find this capital N so that I can make this difference less than that epsilon you chose, then I've got the limit, all right? In the event that this limit exists, right? In the event that this limit exists, right here, then we say that little f here, this function f, is an integrable function over the region R, right? If this limit exists, then the function is integrable. And the value of that limit is the value of the integral. So anyway, I want you to take a look. The book looks at this as well. These epsilons and deltas, or in this case, epsilon and capital N, are just helping you to get an idea of what do you mean by close. Although one thing I want to point out here is that the limit as x goes to infinity, I think of that as x is getting close to infinity. You don't really ever get close to infinity. You just keep getting bigger and bigger. And that's why this isn't, where here you're talking about x minus a is close, right? It's less than delta. You're not saying here x minus infinity is less than something. That's kind of silly. But you just say when x is big, right? X is bigger than some n. So there you go. A little bit more theory on what all's happening here.